Okay, so this is the 8th lecture in advanced course in classical logic. And today we consider ultraproducts of models, of first order models. And the main theorem in this field was theorem. First, some words about sequences or direct products. So we know the definition of direct product of two sets or Cartesian product of two sets, of three sets, the set of all triples. If we have many sets indexed by natural numbers, then again we know what is the direct product, the Cartesian product of them. It is denoted by this symbol, and it is the set of sequences, of infinite sequences, such that nth element of this sequence belongs to the set Dn. The question is, what is a sequence in this definition? First, for simplicity, let us assume that these sets are the same, all the same. Then a sequence, so we have many places. Each place is indexed by some natural number. And at each place, we have an element of D. So in fact, this sequence is a function from natural numbers to D. And we denote its value x of n by xn. And the whole sequence we denote by this notation. So in the case when all sets are the same, a sequence is just a function from natural numbers to this set D. In general, if we have different sets, arbitrary sets, what is a sequence? It will be again a function from natural numbers to what?
Maybe to union of these sets.
To the union of these sets. Yeah, so we need some set that has all elements from all Dn. So it is a union, of course. And we will call this sequence n sequence because it is indexed by numbers from n, by elements of n. And again, its nth element is denoted by xn. But there is no specific property of natural numbers. We can do this for any collection of sets, di, indexed by some set I. And there is, we didn't need that the natural numbers have some natural order, 0, less than 1, less than 2, and so on. So we can consider sequences indexed by any set I. We cannot write them in a linear notation, x0, x1, x2, but nevertheless, we can write like this, and this will be a function from the set I to the union, such that the ith place has the element from Di. So in general, we call them I sequences, and these are n sequences indexed by natural numbers. So in general, a Cartesian product or direct product of some family of sets is denoted by this again, and this is the set of all sequences, I sequences, the set of all I sequences of elements of these sets. So this is what we see here. By the way, here we start with a collection of sets indexed by some set I. This is again a sequence. So we start with a sequence with an I sequence of sets and build a Cartesian product, which is the set of all I sequences of their elements. So I sequences are, so we have two I sequences here. Okay, so now we know what is a Cartesian product of any collection of sets, not only sets indexed by natural numbers. Okay, so here is again the definition of a filter from the previous lecture. This is a collection of subsets of some set I that contains the whole set I, doesn't contain the empty set, is closed under supersets, and is closed under intersection of two sets. If two sets belong to phi, then the intersection belongs to phi. And then ultrafilter is a filter that satisfies additional property. We have two equivalent properties. It is a maximal filter, which means that there exists no filter that is greater than phi. And equivalently, for any set X, either X belongs to the filter or its complement belongs to the filter. Complement with respect to the set I, of course. So these filters and ultrafilters were studied in the previous lecture, and now we will use them. So first we take some ultrafilter phi. So its elements are subsets. Now let us take many sets di indexed by the elements of I. First we take the direct product, and then we introduce the following equivalence relation for any two I sequences, A and B. We will say that these two sequences are equivalent modulo phi if the set of indices where these two sequences are the same are equal. This set of indices is an element of phi. So this is an equivalence relation. It is reflexive, symmetric. This is obvious. And transitivity, one can easily show transitivity. So if a sequence A is equivalent to B and B equivalent to C, then this set belongs to phi and this set belongs to phi. But then we note that the intersection of these two sets is contained in this set, the set of indices where A and C are equal. Because if A and B are equal, AI and BI are equal, and BI and CI are equal, then AI and CI are equal. So this inclusion holds. And therefore, if this and this set are from phi, then the intersection is from phi. And then this superset is again in phi. So this is the easy proof that this is a transitive relation. So this is an equivalence relation. And therefore, we can take the quotient set. Some intuitive terminology. Sets from the filter phi, from the ultrafilter phi, are sometimes called big sets. And this intuition corresponds to the definition of filter. If X is big, then its superset Y is big too. And if we have two big sets X and Y, then the intersection is again a big set. Or another terminology, the set X has at most almost all elements. Then in this terminology, how can we explain this equivalence relation? Two sequences are equivalent if these sequences are equal almost everywhere for almost all indices I. So this terminology resembles something from probability theory. But this is not probability theory. This is just intuitive terminology. So the set of indices that belongs to phi is simply called the set of almost all elements. Okay, So the equivalence class will be denoted by A in brackets. And the ultra product. So here we have a direct product or a Cartesian product of sets defined in the previous slide. And here we define a direct product. So we use the same symbol pi. And here we add the symbol for phi, for the filter, for the ultra filter. In fact, this can be done already for filters. We don't need ultra filter here. We only need that it contains intersections and it is closed under supersets. We don't need the complement. So we simply take the Cartesian product and its quotient set for over this equivalence relation. Okay, so this is the ultra product of sets, but we want to define the ultra product of models. For example, the ultra product of groups, fields, linear orders, and so on. What is a model? So we have a signature that has predicate symbols, functional symbols, constants. Of course, all the definitions that we will give can be given for any signature, but the definitions are quite long. So we will give only some special cases. Let us assume that we have one binary predicate symbol in our signature, P, one functional symbol, F, unary functional symbol with one argument. And we will not write anything for constants. It is an easy exercise to write the same definition for constants. So assume that we have many models, Mi, indexed by some set I. So I belongs to I. So we have sets, di, non-empty sets. And in each model, we have some binary predicate, binary relation that corresponds to this P, and some function, unary function that corresponds to this F. In every model, we have a binary predicate and a unary function. Now we will build the ultra product of these models. It is called the ultra product of models Mi, modular and ultra filter phi. So it will be denoted like the ultra product of sets. So this symbol pi, we write phi here, and we write models Mi here. It will consist, of course, of a set and of interpretation function. So the set, we already know what is the set. The set is the ultra product of sets. So the domain of our model will be the quotient, not the direct product, not the sequences, but the classes of sequences. And on these classes of sequences, we will now define some new binary relation that corresponds to P, and some unary function that corresponds to phi, to F. So for P, we need to say when two classes of sequences satisfy this binary relation P. So P star. So P is a symbol in our signature. P star is a concrete binary predicate over this set D. So it contains some pairs of elements of D. And elements of D are classes of sequences. So A in bracket, B in bracket. So the question is when these two classes of sequences belong to this relation. By definition, this holds if and only if the set of indices such that the corresponding pair AI, BI has this binary relation P in the model I. The set of these indices is an element of phi. So in other words, these two sequences this pair of sequences satisfies this binary property if and only if their components satisfy this property. So almost all their components satisfy this property. The set of indices where this property is satisfied is an element of filter. This is, we can equivalently rewrite. In this big model M, this property P holds for two elements, for two classes of sequences, if the set of indices I for which in the model number I, this property holds for AI and BI, for the components number I. So this set of indices is an element of phi. So this property P holds on almost all components. Or this property on these components holds in almost all models. And now similarly for the functional symbol, we have a function symbol with one argument. So we say when the value of f on this element, a in brackets, e is equal to this element, b in brackets. This holds if and only if the value of f on the element ai equals to bi in almost all models. The set of indices belongs to phi. And similarly, you can introduce definition for constants. A constant will be a sequence such that its elements are almost all the interpretation of a constant. So just write this definition yourselves. Okay. The question is why this definition is correct, or in English it is why this definition is well defined. So we want to define this property P for two elements of our D. Sequence, one class of sequences, another class of sequences. The definition says, take any sequence A, any sequence B from these classes, then check this property. If this holds, then this holds. But why this property does not depend on a sequence? For example, if we take sequence A and sequence A prime that are in the same class, their classes are equal. And similarly, sequence B and sequence B prime in the same class. The question is why this property for A's and B's is equivalent to the same property for A prime and B prime. This equivalence, of course, is symmetric, so we only need to prove one direction. And one direction is easy, like in the proof of transitivity. We only need to use this inclusion. Because for any I, if AI is equal to A prime I, and BI is equal to B prime I, and for the same I, in the model MI, we have this property, then of course we can replace equal by equal. Therefore, this will hold. So any element I that belongs to this set, and this set also belongs to this set. So if two sequences are equivalent, they have the same class, then this first set belongs to phi. Similarly, this set belongs to phi. Now, if also this set belongs to phi by our assumption, then the last set belongs to phi. So we obtain the conclusion. Okay, this is the same is written here. So if three sets are in our filter, then the intersection is in our filter, and then the superset is in our filter. Okay. Now the main theorem in this field, proved by this Polish mathematician. His last name is pronounced not losh, but wash. It is Polish pronunciation. This Polish letter L. Let us recall again one line from the definition of ultraproducts for binary relation pi, a binary relation P. This P holds for two classes if and only if this P holds for almost all components. This main theorem, Losch's theorem, says that the same holds not only for this small formula P of xy for predicate symbol and then two variables, but for any formula. Of course, if we want to formulate it for any formula, the formulation will be rather long. So we will formulate for one special case where we have a formula A with two free variables, x and y. And so we will substitute some element, some A in bracket for x, some B in bracket for y, and here similarly. Okay. The main theorem. So assume we have many models, Mi, indexed by some index I, index set I. We have built the ultraproduct, like in the definition before. Then, for any formula, in our case, for any formula with two free variables, this formula holds on two elements of our ultraproduct, if and only if this formula holds for their components almost everywhere, for almost all indices I. So in the model M, we can substitute for x and for y some elements of the product, of the ultraproduct. Its elements are classes of sequences, so A in bracket, B in bracket. In the model Mi, we can substitute for x and y elements of the model Mi, which are the components Ai and Bi. Okay. Let us, before proving this, let us notice what does this theorem mean if A is just a closed formula, if it does not have free variables. But then on the left, we obtain the formula A holds on the model M, if and only if here the A holds for almost all models Mi. So this is the main thing to remember. If we build the ultraproduct of models, then any closed formula or sentence holds on the big model, if and only if it holds on almost all models. In particular, if A holds on all models, so this set of indices will be just I. Of course, it is an element of the filter, of the ultra filter. Therefore, the same sentence will hold on the ultraproduct. In particular, if A is the conjunction of all axioms of fields. So if every Mi is a field, then the ultraproduct is a field. Similarly for groups, for linear orders, for Boolean algebras, for any structures, that are defined by some first order closed formulas. Okay, so here's again the main theorem. And of course, the proof goes on by induction on the complexity of this formula A. Of course, when we decompose this formula A into smaller formulas, we remove quantifiers, remove conjunctions, negations, then we can obtain bigger and bigger lists of free variables. Of course, the proof will have many long expressions with many free variables here and so on. But we will simplify notation sometimes. Okay, for negation. So for atomic formulas where A is just a predicate symbol P, this holds just by definition of the ultraproduct. This was our definition. Now we need to consider the constructions of negation, of conjunction. We don't need disjunction because it is expressible from conjunction and negation. And one of the two quantifiers, we will consider the existential quantifier. Okay, for negation. So A is the negation of B. So let us denote the set of indices where B holds by X. Now, the set of indices where the formula A holds, MI holds not B, is exactly its complement. So in every model, either the formula B holds or its negation holds. So this is exactly the complement. But we remember one of the properties of a filter, namely of ultrafilters. Here we need that phi is an ultrafilter. So X is an element of phi if and only if its complement. So X is not an element of phi if and only if its complement is an element of phi. This is the main property of ultrafilters. And this will be used in our proof. So in model M, formula A holds if and only if, and in model M, not B holds, which means that our set X, so by definition, the set of this set X does not belong to phi. This is equivalent to saying that its complement belongs to phi. And this exactly means that our formula A, which is not B, holds in almost all elements. So the principal thing is that here we use this property of filters. For conjunction, again, we will use some property of filters, namely the following fact. If the intersection of two sets belongs to the filter, if and only if both sets belong to the filter. One direction from right to left is the definition of filters. It is closed under intersection. The other direction holds because X intersection Y is a subset of X and a subset of Y. So phi is closed under taking supersets. So I guess you can easily write the definition. In M holds A, if and only if, then you use this equivalence, if and only if. In M holds B, and in M holds C. Notice that we already used the properties that phi is closed under intersection, under superset, closed under superset. It respects the complement, so that is a maximal filter. But we didn't prove so far the theorem for the existential quantifier. The question is what property will be used in this proof for quantifier? Well, let us see. So our set A corresponds. So our formula A has the form that exists Z, B, Z. This formula A holds in the set of indices I. In the models MI for some set, so I belongs to X. If we remove this quantifier, then it will not be a closed formula. It will be a formula with free variable. So we can substitute some element in brackets. And this formula will hold in each model mi. In some, for some models it will hold, for some it doesn't hold. So it depends on the sequence C. So the set of indices where this formula holds depends on the index C. So we introduce xc, the set of indices I, such that in mi, the formula B of C is true. B of Ci is true. And so if we analyzed what we need to prove, then we obtain, in fact, the following. The set X belongs to the filter if and only if there is some sequence. So C is a sequence, an I sequence of elements. There is some sequence such that XC is an element of phi. This is what remains to prove. And in fact, this property star follows from two simpler properties. Every set XC is a subset of X, and for some C, it is exactly X. So all these sets are subsets of X, and some of them is exactly X. If we prove this, then star is proved, because so 1 and 2 imply star. Because if X is an element of phi, then by 2 there is some C that is an element of that is equal to X. So this C is an element of phi. So we prove that there exists C such that XC is an element of phi. Conversely, if some XC is an element of phi, then of course X is an element of phi because X is a superset. Phi is closed on the supersets. So the only thing is to prove these 1 and 2. They are a little bit technical, so I will skip the details. Let us simply analyze what did we use to prove our theorem for existential quantifier. We only used that here, that if some set is in phi, then its superset is in phi. So phi is closed under supersets. The question is, what property of filters do we need if we want to prove, if we want to write an explicit proof for the universal quantifier? We didn't write the proof for the universal quantifier because the universal quantifier for all is expressible from the existential quantifier and negation. So we don't need to prove it. But if we want to, if we nevertheless write the proof for the universal quantifier, what do we need? Which properties of filters do we need, of ultra filters? So this is an exercise to think for the listeners. Okay, so in some simple form, so using some simplicities, we proved this main theorem. So let us recall again. So if A is a sentence, it's a closed formula, then this main theorem states this fact. A formula, a closed formula, holds in a model if and only if it holds in almost all models Mi. So the set of indices where it holds is an element of phi. It's an element of ultrafilter. So in particular, if we have many formulas A, which is called a theory, as an arbitrary set of sentences, and we had many models Mi, then if all models satisfy this theory T, then the big model satisfies the theory T. So the ultraproduct satisfies the theory T. So this is what we expected. The ultraproduct of some models that satisfy, for example, the axioms of fields, the axioms of rings, and so on, are again fields, rings, Boolean algebras, linear orders, and so on. So the ultra product of groups, fields, linear orders is again a group, a field, a linear order. Let us think about the following very special case. Assume that all models MI are just the same. Like in the usual arithmetic, we can multiply two numbers, A times B, but we can multiply the number with itself, A times A, and do it again and again, A times A times A times A. Here we can also take the same models. All M models MI are the same models. M is not good to denote. But anyway, all models are the same. Let us denote them M. It's not the same M as here. Then the ultra product has a special name. It is an ultra power. And we will denote it like this, M phi. Then from this theorem, so in this theorem, only two cases are possible. The sentence A either holds in all models MI, or it holds in no models MI. So this set of indices is either the whole set I or just empty. And therefore, this condition on the right simply means that A holds in the model, one model MI, they are the same, if and only if it holds in the ultra power. So this is what we write here. For any sentence, a model and its ultra power satisfy exactly the same closed formulas. Usually it is written as follows. Two models are equivalent for first order language. They are elementarily equivalent. We already studied this relation when we studied games, reinforced games. So the main conclusion, the ultra power is an operation such that if we start with some model, we obtain a new model, but the first order language cannot notice the difference. These models satisfy the same first order closed formulas, the same sentences. In today's lecture, we did not notice the equality predicate. Of course, there are languages with equality, but if you consider the signature with equality, the language with equality, then the same theorem can be proved. In particular, for the equality, the same theorem holds. This is an easy exercise, in fact. So if all models are normal, which means that the equality is just a true equality, the coincidence of elements, then in the ultra product it is again the coincidence relation, and so the ultra product of normal models is a normal model. It is a task for listeners. And here's an interesting task. For example, assume that all models are have two elements. Now we take the ultra product. We have many models, but all of them are two elements. How many elements do we obtain in the ultra product? If we take just product of two element sets, for example, if I is the set of natural numbers, then we obtain continuum many elements. We have all sequences of two element sets, of two element, all possible sequences where we can use two elements. But the ultraproduct is not just a product. We use the equivalence relation. We collapse some elements. And it turns out that we collapse very many elements. We obtain only two elements in the ultraproduct. So this is a task. And of course, this theorem can be generalized to some other languages, but not all languages are so good. For example, if we consider first order language with infinitary conjunction, we can build conjunction of infinitely many formulas. This is quite a good language, an expressible language, but this Wash theorem doesn't hold for them. So if we build ultraproduct, then it doesn't preserve properties that are formulated in this infinitary first order language. So only for some languages this theorem holds. And in fact, this theorem is a reason for compactness, as we saw at the very beginning, before the lecture. Compactness can be proved using ultraproduct. In the next lecture, we will see how to make a bridge between Wash theorem, ultraproducts, and compactness. So this will be the main consequence of this Wash theorem. Okay, so this is the end of the lecture. We can discuss some questions.